Today we're going to start off with a talk called Fuzzy Multi-Criteria Optimization. Obviously it will be in Python, but it will contain a little bit of Mathematica for those of you who might have dabbled a little bit in it. It would be a good fun. I'll show you the interaction between analytical engine-based computing platform versus the Python platform that we know and love. Right. So I'm happy to be here for the second year. Last year we had a presentation. It was on using Graph-Theoretic network centrality analysis, and I was demonstrating how it can be done very easily on the Python library of network X. Okay, and we kind of proved beyond shadow of a doubt that the most network-centric or the most central figure in Hollywood is apparently Robert De Niro. If you remember recall the talk from last year. Right, so as you can see from the title, it's got really three elements to it. One is the basic underlying problem, which is what I call the portfolio optimization problem. I spent a little bit of time discussing it because a lot of us are not really from financial background. So you can think of it as a bonus MBA on investment management, as it were. The second element is the fuzzy multi-criteria. This is the mathematical enhancement that we came up with. And finally, of course, the last bit is how it's done in Python. And again, maybe with a little bit of Mathematica to add to the flavor. Right. So what are we talking about? Basically, the investment management problem is you have 100% of fund. Okay, this is what you want to invest, right? And you have n possibilities. In other words, you can, if you think of stock, I think most people are familiar with stock, but in modern financial industry, we think of it in more general term like investment vehicles. But if you think of having n stock to invest, you should buy maybe 1/10% in each. That's the uniform distribution, right? Or you can be a stock picker. You can invest 100% in one stock and ignore the rest, the n-1 stock. Or you can come up with a way to optimize it. Okay? Either way, or any way you come up with, the solution that you are going to be working with is what's called a weight vector, which is a non-negative continuous value from 0 to 1, and sum of all the elements adds up to 1. So I'll get out my lightsaber. Okay? So that's how you define your solution space, right? It's non-negative because in stock you cannot short sell. You have to invest. It has to add up to 1 because it's 100%, right? And n is the number of investment vehicle you have to play with. What you like to do is you maximize return, obviously, and that's done by a weighted sum. So that's just a dot product between the return expectation and the allocation in each investment vehicle. But that is the notion of risk. Now, risk basically is the variance or volatility of return. But because you're not allocating your investment in just one stock, your return is actually determined by how you allocate. So that's given by this quadratic form, X transpose sigma. Sigma here is a variance covariance matrix, X. Okay? So basically, these two criteria, this bi-criteria, kind of work against each other, right? You want to maximize return, but you want to minimize risk. Okay? So how do you do that? Well, classically, there are actually three equivalent way of dealing with it. One is to say, well, tell you what, let's just have some kind of risk tolerance and make it a constraint, a hard constraint. I cannot tolerate more than this much variance or equivalently volatility. Volatility in finance basically is the standard deviation. So it's the square root of this quadratic form. Alternatively, you can say, well, let's have a return target. I don't want expected return of the portfolio to be less than, say, 3%, and try to minimize as much risk as you can. And finally, the third option is to say, well, let's think of it as a weighted objective function. There's criteria 1, there's a criteria 2, and you maximize some kind of weighted sum of both. Okay? And this really formed the basis of of everything, of all the investment management in the last 60, 70 years, okay? As you can see, it's called modern portfolio theory, but it was modern in the sense of 1952, 59, okay? So that's the problem. Now, I'm trying to make the presentation a little bit of everything for everybody. So I'll talk at the top level, but at the same time, those of you who are more into the math and feels hungry if you don't have a little bit of equations in the morning, this is to feed you guys, I guess. So basically, this one represents I think the second option, right? You set up some kind of a constraint on the return objective, and then you minimize the risk. Now, you want to say that weighted return is, say, no less than 3% per year, 4% per year, 5% per year, and so forth. And what you have to do is transfer this inequality into equality constraint, right? And then put them together in a Lagrangian. Obviously, you have two Lagrangian multipliers, one to define the weight solution, one for the return target. Then you maximize you take differentiation, right? Partial differentiation with respect to the Lagrangian. You clean up bits, and you end up with essentially a reparameterized form of either a hyperbola or a parabola, depending on what you put on the x-axis. Basically, this is it. This is a return. You want to go as high as you can. This is the risk axis. You want to go as little as you can. So basically, you want to go into northwest corner, right? And you have this curve, which defines what's called Pareto efficient frontier, meaning that once you're on that frontier, it becomes a matter of trade-off. You want more return? Fine, but you have to take on more risk. You want less risk? Fine, but you have to give up some expected return. You can't do better than that. So that is really the state of the art of investment management over the last 40, 50 years, right? And this obviously can be done in any kind of platform. Now, let's see what happened. Let's see what happened in terms of if we bring in more math and more technology, more modeling capability to it. Okay, can we generalize the problem? But first, let's just see what the motivation of the problem is. Okay, now one of the motivation, and we have this in real case, for example in Thailand, the wealth investment sector, sometimes they have their own idea of how they want to shape their portfolio. For example, we can be a good fund manager, but when we go to them and say, well, this is the allocation we give. It's good, it's efficient in terms of Pareto efficiency as per Markowitz modern portfolio theory. But sometimes they may say, well, you know what, but for the next year, I want to go big in financial sector. Okay, for example, just not out of nowhere, but this is their intuition. This is what they want to incorporate. Or if you think about ethical investment, you can have efficient portfolio, but it requires investment in, say, tobacco industry, or in company that's not sustainably model. So the client may say, well, actually, I want to limit my exposure to what I would consider not sustainable sector, right? Sector like maybe like I said, if you are investment on behalf of a cancer research fund, you don't want to find out that your money is going to finance tobacco company, for example, right? Now, some of this can be imposed very easily as a hard constraint. And you saw from the math how easy it is, well, how straightforward it is to implement a hard constraint. You put in the Lagrangian, and you just impose that. But what if your constraint or your criterion is not hard, it's fuzzy? In other words, a client may say, I want to invest no less than 10% in, what's the example I have here? Say something like, okay, I want to invest no less than 10% in a banking sector, right? Does that mean that if the solution comes up with 9.5% investment in banking sector, it completely fails? Obviously not, right? But if you come up with a zero investment, obviously that's not acceptable. If you come up with 50% investment in banking sector, it's more than acceptable. In fact, once you go beyond 10 or 12%, you might as well consider other criterion. So there is a diminishing return in psychology. There's a little bit of saturation point, okay, in the criterion that you can introduce to your problem. Now, let me shift gear and go to something else. I was going to talk about coffee, but apparently there are so many coffee affectionista in the audience that if I bring that example, I'm going to get counterexample. So I'll say, how hot do you need to cook to kill all the bacteria? Okay? Presumably we don't have bacteria aficionados here, so I think this example is pretty safe. Well, I don't want to come up with my own science, so this is what I quoted from Google. It says something about at 122, no bacteria that's pathogenic or causes illness to human being. You can't kill all the bacteria. You just want to kill the bacteria that harm you, okay? And at certain temperature, they stop reproducing. At certain temperature, 99.9% of them die, okay? So what's that temperature? Now, this is exactly what this kind of fuzzy mapping is. You have this temperature in Fahrenheit on this axis, right? And I have this concept, this fuzzy concept. This fuzzy concept say hot enough to kill harmful bacteria, okay? And of course, if it's too cold, it's not hot enough. But at around 100-ish, it begins to be hot enough, and beyond this point, you don't have to crank up the heat anymore, okay? And this is useful because actually, according to some cooking website, if you go beyond like 150, you begin to lose flavor. I know I'm not a very particular eater, so I don't really care. But you can see why it's not one of those where I want to be as high, as hot as possible. And again, it gets back to the coffee. You want your coffee to be hot, but you don't want it to be boiling hot, right? So it's not a maximizing criteria. It's a saturated type of criteria, and it's mapped onto the fuzzy notion of something. This something being the notion that, is it hot enough to kill the bacteria? Okay, okay. And again, so this is the fuzzy function, okay? Now, technically it's called fuzzy membership function because it starts at 0, it ends up at 1. 1 being perfect. So they call this fuzzy membership. So fuzzy set, the set of temperature that is hot enough to kill bacteria. So the temperature in this area obviously belongs to that set, 100% or approaching 100%. This is a sigmoid function, so you never get perfect 1, okay? So it's not 1, 0, yes, no. It's partial yes, partial no. But it's not a woozy kind of anything goes scale, but it's very sharp. It has a mix between sharpness of criterion and smoothness of transition. And that's what the sigmoid function is perfect for. Now, if you notice, as you know, of course, sigmoid function, aside from the coefficient, you use that in your neuron, it has basically two parameters if you think of it as a scalar mapping. One is the stretching, right? How sharp or how smooth, right? And one is where do you put the threshold, right? So those are the parameters that you can actually play with. Okay? What this means is this. What this means is that for this problem, okay, it may come from an expert, right? An expert. So this is kind of like a fixed fuzzy function. You can use this in the rice cooker or for whatever, okay? But for a lot of application, and going back to my wealth segment portfolio management, this kind of parameter, you might want to have it like free form. I may want something, so if you imagine, this is something like return, okay? How much return is good enough for you, okay? Somebody might say, around this level is good enough. Somebody else will say, around this level is good enough. Some people are very critical. They say, it really has to be a sharp edge. Below this, I don't care, I don't accept. Okay? Some criteria or some people may say, well, I prefer a smoother transition so that if you miss return target, it's okay as long as you make it up by having low risk, for example. Okay? So the concept is that we fuzzify objective function. Okay? So that's the concept of the fuzziness, right? You have a scalar objective function that is fuzzified, so you control the level, the target level you have, as well as how critical this objective criterion is. Okay? Now, and this is the fuzzy bit, right? And go back to the Markowitz modern portfolio theory. You already saw that we have two criterion, right? So sometimes it's called bi-criteria model. One is risk, one is return. But if you think about it, if I introduce risk, return, and I introduce something like invest ethically, or invest in banking sector, or maybe additional risk measure. In fact, the example that I'm going to show is going to introduce two more risk criterion. Okay? Risk is not just measured by standard deviation alone. It may be like the probability that you are going to lose more than 50% of your investment, for example. Okay, like max drawdown loss, that sort of thing. So the idea is that traditionally with this Markowitz framework, okay, basically you are bound to have just two criteria, basically two axes. Okay, and you can't have more than that. And like I said, you can only have two ways of dealing with it. Treat it as a hard constraint, or treat it as maximizing or minimizing, meaning as much as you can or as little as you can, but no level setting, no critical threshold. Right. So let's introduce, so to the fuzzy, we saw that fuzzy, we introduced the notion of that. Again, this is some background. Now, I have to be open and honest with you. The mathematics I'm going to introduce here is not all that new. In fact, a lot of it was well, fuzzy is based on Lofty-Zadeh's fuzzy set paper in 1965. And a lot of this multi-criteria back in 96 and 98, I did apply to different kind of portfolio. This was when I was with Chemical Bank in London. We were doing a prop trading. So that means we have to allocate, not into stock, but into different high frequency. So a lot of math was already worked out, okay? But what wasn't there was the mass customization or the wealth segment. So for the longest time, this idea kind of lay dormant because unless you are actually running a prop desk in a bank, it's more than we need, okay? So that's just some picture. Now, let me summarize what this fuzzy multi-criteria adds to the problem. First of all, okay, I'm going to take the modern portfolio theory, which I now assume that you are somewhat familiar with, given that 2-minute MBA type of thing. You used to have bi-criteria, right? Return and risk. Now you can have multi-criteria. Well, technically bi-criteria is multi-criteria, but in this case, I mean more than two, right? You can have as many as your heart desires, okay? Number two, the idea of linear improvement. As much as you can, more or less, the more the better, the less the better. Into fuzzy target, I would prefer risk and return to be above or below so and so. I would prefer commitment to the banking investment in the banking sector to be above 10 minutes or so, that kind of thing. Okay? And then the hard constraint. Okay? These two are sort of like altogether. Yeah, this is the bit where I say, well, instead of having a hard constraint, I want no less than 10% exactly into, I want no less than around 10%. And in fact, you don't want to go to your wealth client and say, be clear, what do you mean? No more than 10% or no more than 9% or no more than 10.1, okay? If the client gives you no more than 10%, you may ask another anchoring question. Well, is 8% acceptable? Yeah. If you say, how about 5%? Well, that's not acceptable, right? Then you can start to parameterize the fuzzy function, right? And this, and finally, and this is the most critical bit of all, once you fuzzify the multi-criteria and you have more than two, you can have 4, 5, 6, 7, 8 criteria. Normally, the way you put them together is just to add them. Weighted additive. If you're a student of multi-criteria decision making, a lot of time is based on weighting scheme. How much does risk mean to you? How much does return mean to you? And just sort of like give a trade-off, right? Well, with fuzzy algebra, literally fuzzy defines its own algebra. You know, it has its own multiplication rule type of thing. For example, instead of saying, okay, this is a screenshot I have to admit this is actually from Mathematica because I do my prototyping in Mathematica. Let's say this is criterion 1. Okay, you fuzzify it. This is criterion 2. You fuzzify it. And if you add certain weight, all right, you get something like this. Okay? So this, you can imagine this is fuzzy criterion 1, this is fuzzy criterion 2, and you add them together. Well, with fuzzy mathematics or fuzzy algebra, you have more options. You can say criterion 1 and criterion 2, right? In which case, you actually form an OR AND gate. Or you can do this, which is an OR gate, right? Which is an OR gate. Let me just show you real quick how this thing works. Right. Where am I? Slideshow. Okay. Right. This thing, I did, okay. Now, if I add a lot of weight to one side, obviously it's indistinguishable. Oh, you're not looking at this, are you? I have to cancel the presentation first, correct? Okay. Right. And then I have to go to here. Right. Now, in this case, what I did was I used this slider to say, I want to care only about objective 2. In which case, whether or not you AND them together, OR them together, or add them together, it's the same thing. I only care about one criterion. Now, what happened? Watch what happened when I did this. This is a manipulated widget, as it were, in Mathematica. Right? So if I give them equal weight, then obviously it matters. Here it's kind of like if you meet one and not the other, it's sort of like halfway, right? You get like 0.5 on score. Here it says, unless both of them are satisfied, I'm giving you a 0. Here it says, as long as you satisfy one criteria, you're good. So it's an OR gate. So all of a sudden, you no longer have to have this kind of trade-off that is basically linear in your trade-off space. You can literally OR gate them or AND gate them together. Now, obviously, this introduces a lot of mathematical complexity if you want to solve it, but I'll show you that in Mathematica and in Python, it's easily doable. Okay, so let's go back to the presentation. We're back? Okay, right. So now let's look at what the whole thing looks like. Hopefully this gives you the background. So first of all, you understand that in investment management, we have this problem of allocating. Historically, there are 2 criteria, expected return and risk. And you have a kind of trade-off that shows itself as what's called Pareto efficient frontier. Looks like a parabola, or hyperbola, depending on what you use for the x-axis. Now, let's just see for some real example. This just, we loaded, I think, 39 investment vehicles. Some of them are actually more like deposit, okay? This is kind of a histogram of their correlation number. So don't worry about this, but it just shows that they're not perfectly correlated. Sometimes some of them are positively correlated, some of them negatively correlated. Now, what I want to show first, though, is that in this example, I'm not introducing additional criteria like investment in banking sector or hospital sector. What I'm going to do is introducing additional risk criterion. So this is the distribution of 39, let's just call them 40 investment vehicle with respect to return, with respect to volatility, risk, and these 2 are like what's called downside risk, okay? This is what's called maximum drawdown. Basically, it's the loss, a very sad scenario, a very bad day. And this is a typical loss, so typically bad day, right? So obviously, it's all negative number, right? You still want to maximize because you don't want to be very far negative. But those are the distribution. Now, right away, you'll see that there's no parametric way of capturing this distribution in an easy way, okay? Now, so let's see how this happens in Python, okay? Let's see how this is Python. Okay, this definition enters here. From SciPy optimize, import minimize, Okay? By the way, there's no maximize. You just have to put minus in front if you want to maximize. And this is what you input as hard constraint. And there are two things. One is hard constraint here, and one's hard bound. Okay? Hard constraint type of constraint is equation. Okay? I put in the lambda function. Basically, the lambda function here applies to this transpose. X is our solution. Dot and numpy dot 1, not 1. Okay? Minus 1. Okay? Must be 0. The way minimize SciPy optimized function does is you put in constraint of something equal to 0. Okay? Like the Lagrangian that I showed you earlier in the mathematical slide in the mathematics, right? So I have x transpose 1 minus 1 equal to 0, and range hard bound x is greater than or equal to 0. Well, actually, hard bound you can put in between 0 and 1. Obviously, if it sums to 1, each of them cannot exceed 1. Okay? So this is how you actually hard bound. This is how you hard bound your constraint, right? These are basically the vectors that I'm going to be using later on. Okay? And that's the file. Right. So, first, let's replicate Markowitz, right? Just to see that we can do it. How do we do this? Well, again, what I do is I enumerate over the threshold. This is how you fix the return threshold target. You have to be sensible, right? Your return target cannot be higher than the highest return investment vehicle in your universe, right? If your investment vehicle ranges from 1% to 8%, you can't say, I don't care, invest in any kind of allocation as long as the weighted sum gives me return greater than 9%. And that's not going to be feasible. So obviously, it's somewhere between 1 and 8. And what I do is I just chop them up into even interval and start enumerating, right? So let's just say that a return has to be greater than 1%, return has to be greater than 1.5, has to be greater than 2, 2.5, 3, and so forth. And this is how you enumerate finite points of the efficient frontier. Okay, so that's what this is. For every threshold in threshold return, I set the threshold return. Now this is where I create a list of solutions. Okay, frontier MPT is a list of solutions. So optimization, I have hard constraint defined from the previous slide. Now I introduce the inequality. This guy, x dot return minus threshold. This guy, right, has to be greater than or equal to 0. Type inequality. Again, the way the SciPy. So I enumerate them, okay? And now I call the function minimize, okay? Minimize. Now, what is this? This is the quadratic form. Basically, this is I defined earlier just to make it useful. It's just that. It's very simple, but it looks a little bit long when I type in. So I just put, okay, so it's basically x transpose the matrix times x. X transpose the matrix times x. So I multiply the matrix times x first, then I pre-multiply by the x transpose. So that's the quadratic form. So basically that, I keep adding to this list additional solution for every level of threshold, right? From low to high or from high to low, I don't remember which, right? And plot the scatter plot. It looks like this. So that's the solution. Now normally, when you plot on the x-axis, you take the square root of the variance so that you get the standard deviation as your unit. Okay, so that's your thing. Okay, so that's that. Okay, so obviously, it sounds silly, but obviously with SciPy you can do the fuzzy, you can do the Markowitz efficient frontier, right? Okay, now next step. Well, let's do this. Before I add fuzzification and multi-criteriality, let's just introduce the fuzzification, right? Now, if I introduce the fuzzification, and the fuzzy is a monotonically increasing function, right? I should be able to replicate exactly the same solution set, because it doesn't matter if you're maximizing return before you fuzzify it or after you fuzzify it, it's still the more the better, correct? So this idea that risk and return exist as a trade-off in the Pareto frontier shouldn't change. Just because you fuzzify risk and fuzzify return, right? And this is what it does. Basically, I introduced the fuzzy function, fuzzification function. Basically, use logistic sigmoid. Everybody's happy with. Now, and here's where it gets tricky. I have to introduce, because normally your parameterization is taken care of by the learning algorithm. This is not. This is about the preference of your investor. So I have to anchor. Basically, this means that a fuzzy good is about 0.95. So if 1 being perfect, 0 being completely bad, you can say, what is fuzzy bad? Fuzzy bad is like 5% or 0.05. What's fuzzy good? Fuzzy good is like 0.95, okay? So that's basically asking this parameterization, this thing, okay? What level is fuzzy good? Fuzzy good meaning 0.95. What level is fuzzy bad? Fuzzy bad meaning 0.05. Okay? Those are the two anchor points that you need for the logistic sigmoid. Now let's get back to our problem. Okay? Now, I haven't gotten around to making the widget for Python, but it's doable in Python. But the example I will show you is in Mathematica because it's quicker for me. Right? But basically, that allows for parameterization. But for the purpose of this talk, let's just say that there are three, the kind of parameterization you allow is this. Okay? For whatever criteria you have, okay? There's the worst, there's the best. Let's take return. Let's assume we have between 1 and 8%. Okay? All the 40 investment has between 1 and 8%. What I do is this. I offer 3 levels of thresholding. You say, well, let's line them up and look at the median, right? Median of all the 40 investment vehicles. Let's say the median is 4.5, right? Then I look at 10% quartile and 90% quartile, meaning the bottom 10% and the top 10%, right? So let's say the bottom 10% has about 2.1, right? And the top 90th percentile is about 7.5. So those are the 3 thresholds that I'm going to offer as a parameterization option, right? Now, in reality, you can do this infinitely, right? Between 0 and between 1 and 8. But I'm just going to say 3 levels, okay? 1 is neutral, meaning that let's just make a criterion anchored at the median, right? The other one is let's anchor it easy, just the bottom 10%. The other criterion is to make it hard. You know, I don't care. You know, you can allocate any way you like, but it has to be no less than what did I say as a 90th percentile? 7.5, let's say. Okay, so that's aggressive. That's harsh. I call it harsh. So 3 settings. 1 is neutral, 1 is easy, 1 is harsh. Okay. As for the slope, I use this to define the fuzzy good, fuzzy bad, so the slope is taken care of. Right. So those are the 3 anchoring. Now, let's see what happens. These are actually the numbers from our data. So this is, you don't have to care about what that means. Basically, this is return. The more to the right, the better, and I fuzzify it. This is risk. Okay? The more to the left, the better, and I fuzzify it. This is also risk, but this is like a negative return. So I still want to be the more to the right, the better. And this is typical loss. So this is like this, except it's not as severe. You can see this is like 80%. This is really, really, really bad, like losing 80% and so forth, right? So that's that. So the 3 colors are the 3 anchoring point. And there. So first thing first was, if I fuzzify the 2 criteria, but I don't introduce the other 2, do I replicate Markowitz? Yes, it does. Okay, so that's the orange. It's basically repeating the same line. And now, with 5 minutes to go, let's speed this thing up a little bit. Right, so I can do AND gate, OR gate, and so forth. Well, just trust me that it works. Okay, basically, the fuzzification you can do many ways. You can add. Let me go back one slide just to make sure. Okay, if you add, right, basically you just add dot weight. If you add them, you actually take the power, right? Okay. And if you want to do OR, you also take the fuzzy function and you raise them to the power, but you take -1 of that. Okay, so you have 1 minus and so forth. Okay, so come to me if you're really into this thing. Okay, but it's there, and I'll share the code if you like. Just email me. Okay. Now, basically, this is what to wrap up things, the discussion. This is what you end up with. Okay, this is a different parameterization scheme. If I put in, say for example, hard neutral. Okay, yeah, the rate dot represent the bigger they are, the more weight I give them. Okay, these are the 4 criteria. The further out they are, the harsher the criteria. So this is very hard. I push them all the way out. This is kind of easy. Harsh, neutral, easy. Okay? But this one, I only make return harsh. Volatility, harsh. But the max drawn down criteria, I go easy on that. Okay? Typical loss criteria, I go easy on that. And you can see that the solution that's optimized actually reflects exactly this. So somehow it's able to iterate and optimize to find a solution that fits the profile. This is what I mean by the new wealth investment. They don't want just generic portfolio allocation. They want something that suits their preference. Okay? And their preference is indicated by the red dots. And the solution is indicated by this. Okay? And this is for different anchoring scheme, right? Like harsh, easy. Now this is, I vary different things. Weighting scheme, for example. Like this guy, instead of caring about return like previously, I care so much about max drawdown, right? These are guys who are very nervous about low side risk. So obviously, it's satisfying that criteria. So the solution is achieving that objective, okay? And this is a little bit more interesting, but takes a long time to explain. This is comparing different weighting schemes, whether you add them, you multiplicative AND, or you multiplicative OR them, okay? And the interesting bit is that if you OR them, sometimes it just ignores, right? This guy is very important, right? But because you can OR them, it gets ignored because it finds a better solution, a richer solution by focusing on the other 3, okay? Now this is the bit that is in Mathematica. I'm not going to bother. Is what you saw. Basically, the widget is much quicker. Well, Mathematica can do analytical, and this was the demonstration that we did. But the way I work, unfortunately, because I'm very old, I came from a generation where Python is not hip yet. So what I do is I tend to prototype things in math. Because mathematically it's very powerful. And then I asked this guy, Poomjai, who helped me to translate Mathematica. So he's a machine translation guy in my team. And finally, we are hiring. Okay? We are hiring. SCB is hiring. We are probably the oldest. Just allow me a few seconds. We're the oldest financial institution in Thailand and hope to be the most forward-thinking institution in Thailand. Okay, and email me, email the team. We have a booth upstairs, and if you're looking for something interesting and you're looking to be challenged, okay. So thank you very much for having me. It's a very special year. The first time I have my own son somewhere sitting in the audience. He just began his Python journey early this year. So hopefully he will get a kick out of this getting together. And please, approach any one of us with any question. And I don't know if the organizer will have the slides upload somewhere, but I just put in all this kind of glossary that we use, or I use, to define, what's business intelligence, what's data analytics, how does AI different from computational intelligence, which is where my background is, and so forth. And so we'll have this available. Again, code as well, okay? Just email us, email me, and we'll share everything. Okay, we'll share everything. Thank you.